Today, we embark on a journey beyond the familiar hum of electronics, into a realm where computation is forged not from an electric current, but from a pure beam of light. This is the story of how we hit the absolute limits of a technology that defined the modern world, and how in our desperate search for a way forward, we taught light how to do the one thing it was never meant to do: remember. For over half a century, humanity witnessed a miracle. It wasn't a single event, but a quiet, relentless prophecy that fulfilled itself year after year. It was called Moore's Law. The idea, first observed by Intel co-founder Gordon Moore, was breathtakingly simple. The number of transistors we could fit on a silicon chip would double roughly every 2 years, and for 50 years, it held true. Think about what that meant. The room-sized computers of the 1960s, with their blinking lights and whirring tapes, gave way to the beige desktop boxes of the 90s. Those in turn shrank into the sleek laptops, and finally, into the supercomputers we now carry in our pockets. Every generation of technology was a giant leap. Your smartphone today possesses more raw computing power than all of NASA had at its disposal when it sent humanity to the moon. This relentless shrinking was the engine of progress. It fueled the internet revolution, the mobile age, the dawn of social media. Every digital convenience we now take for granted rests on this single beautiful principle of miniaturization. But a promise that lasts forever isn't a law, it's a fantasy. And we were beginning to wake up from the dream. The problem is one of scale. We pushed silicon to its breaking point. Today, the most advanced transistors, the tiny on-off switches that form the basis of all computation, are measured in single-digit nanometers. To put that in perspective, a single human hair is about 100,000 nanometers wide. A strand of your DNA is about 2.5 nanometers wide. We are now building circuits where the components are only a few dozen atoms across. At this surreal atomic scale, the orderly world of classical physics dissolves into the bizarre and unpredictable realm of quantum mechanics. The very barriers designed to keep electrons in their designated paths begin to fail. This phenomenon, known as quantum tunneling, is where electrons simply leak through solid walls they shouldn't be able to cross. Imagine trying to build a fence to hold in a mist. The particles just drift right through. In a chip, this leakage is catastrophic. It creates errors, corrupts data, and renders the computation unreliable. It's like trying to have a coherent conversation in a room where everyone is whispering at once. And then there's the heat. Every time an electron moves through a wire, it generates friction, which creates heat. When you have billions of transistors crammed into a space the size of a postage stamp, all switching on and off billions of times per second, the heat becomes biblical. It's not just warmth, it's a suffocating inferno at the microscopic level. This heat death can warp the delicate architecture of the chip, slow down its performance, and, in the worst cases, melt it into slag. We've had to invent increasingly complex and power-hungry cooling systems, fans, liquid cooling, entire water-chilled infrastructures, just to stop our most powerful machines from cooking themselves to death. We hit the wall. Pushing further wasn't just difficult, it was becoming physically impossible. Physics itself, the very foundation of our engineering, was now the obstacle. The Silicon Age, the bedrock of our modern civilization, began to show its cracks. The engine of progress was sputtering. Just as our tools began to fail us, our ambitions soared to new heights. We weren't just content with faster spreadsheets and better video games anymore. We had set our sights on the grandest prize of all: creating artificial intelligence. And this new ambition came with a voracious, insatiable appetite for power. If the Silicon Age was a steady jog, the AI revolution is an all-out sprint. Training a large AI model, like the ones that power advanced chatbots, generate stunning art, or help scientists discover new medicines, is one of the most computationally intensive tasks humanity has ever undertaken. It involves feeding a neural network trillions of data points and having it adjust billions of parameters over and over until it learns. The energy required to do this is staggering. We don't measure it in the wattage of a light bulb anymore. We measure it in the energy consumption of entire cities, even small nations. The vast, sprawling data centers that house these AIs are the new industrial heartlands of the 21st century. But they don't forge steel. They forge intelligence. And they blaze with the intensity of 1,000 suns. Imagine a warehouse the size of several football fields, filled with endless rows of humming servers, each packed with the most powerful processors money can buy. Now imagine that every single one of those processors is running at full tilt 24 hours a day, generating so much heat that colossal air conditioning units and water cooling pipes as thick as a person's torso are needed just to keep the facility from bursting into flames. The carbon footprint of training a single, top-tier AI model can be equivalent to hundreds of transatlantic flights. This is the great paradox of our time. Our quest for a higher, more abstract form of intelligence has chained us to a brutal physical reality. We are trying to build the future, but we are powering it by burning the present. Our pursuit of knowledge has collided head-on with the physical limits of our planet and our tools. The silicon chip, once our greatest asset, was now becoming a liability, a bottleneck not just for speed, but for the sustainable future of our civilization. The question was no longer just, can we build it? It was, can we afford to? When you hit a wall, you have two choices. You can keep pushing against the bricks, hoping for a different result, or you can look for a door. For decades, we pushed. We tried new materials, new chip architectures, new cooling methods, but these were incremental gains, small patches on a failing system. The wool remained. It was time to look for the door, and that door, perhaps, was not made of matter at all. The answer, some visionaries proposed, was not in electrons, but in light. Let's step back and think about the fundamental difference. An electron is a particle with mass and a negative charge. To make it move, you have to push it through a physical medium, a copper wire, a silicon trace. As it travels, it collides with atoms, jostles its neighbors, and generates friction. It's like trying to run through a dense, muddy forest. You'll get there, but it's slow, messy, and you lose a lot of energy along the way. A photon, a particle of light, is a completely different beast. It has no mass and no charge. It is pure energy. It doesn't crawl, it travels at the ultimate speed limit of the universe. When it moves through a medium like glass or a fiber optic cable, it does so almost without interaction, without friction. It's like a ghost passing through a wall. It is fast, clean, and impossibly efficient. We already trusted light to carry our information across vast distances. The global internet is built on a network of fiber optic cables that flash pulses of light across continents and under oceans, carrying our emails, video calls, and every bit of data that connects our world. We were using light for communication. The revolutionary idea was, what if we could use it for computation too? The dream of photonic computing began to take shape. A computer where information wasn't a sluggish current of electrons, but a brilliant, instantaneous flash of photons. A machine that could calculate not at the speed of electricity, but at the speed of light itself. The theoretical advantages were mind-boggling. It promised a world without heat death, without electronic traffic jams, a world where the only limit to speed was the very fabric of space-time. It was a beautiful, elegant vision. A way not just to climb over the silicon wall, but to leave it behind entirely. But every beautiful dream has its harsh awakening. And for photonic computing, the awakening was a single, devastating flaw. Light is a masterful messenger, a brilliant calculator, but it has one fatal weakness: it cannot remember. Think about how a normal computer works. It has a processor, the CPU, that does the thinking, and it has memory, RAM and storage, that holds information. The processor constantly fetches data from memory, performs a calculation, and then writes the result back to memory. This ability to store a state, to hold on to a 1 or a 0, even when the power is off or the calculation is finished, is the absolute bedrock of computing. Without memory, a computer is just a glorified calculator that forgets the answer the instant it finds it. Its results would vanish like whispers in the wind, like ripples in a pond that disappear a moment after the stone has landed. Light, by its very nature, is transient. It is always in motion. A photon is a particle of go. You can shine a laser beam through a logic gate and get an answer, but as soon as the beam passes, the information is gone. There is nothing left behind. It's like trying to write a novel with a pen that has no ink. You can go through the motions of writing, but the page remains blank. This was the missing link, the chasm that separated the dream of photonic computing from reality. For years, this problem seemed insurmountable. Researchers could build photonic components that performed calculations faster than any electronic chip, but they couldn't build a complete computer because they had no way to store the data. The only solutions were clumsy hybrid systems that used photons for processing and then converted the signal back to electrons for storage. But this conversion process was slow, inefficient, and power-hungry, completely defeating the purpose of using light in the first place. It was like owning a race car, but being forced to stop and get out to push it every few feet. The promise of a new era of computing faltered on this fundamental obstacle. Light could talk, but it couldn't think. Because to think, you must first be able to remember. And then, as is so often the case in the history of science, the breakthrough came not from a single dramatic eureka moment, but from the patient and brilliant work of scientists combining two seemingly unrelated fields of technology. They found a way to trap light and, in that cage, teach it how to hold a thought. The first piece of the puzzle was a device called a microscopic resonator. Imagine a tiny, perfectly crafted ring of glass on a chip, smaller than the width of a human hair. When a beam of light is guided into this ring, it doesn't just pass through, it gets trapped. The photons begin to circle around the inside of the ring, racing around the track over and over again, like a caged star. This elegant little structure was the first step. It gave scientists a way to hold on to light, to stop it from simply vanishing. But trapping the light wasn't enough. They needed to give it a way to record information. This is where the second piece of the puzzle came in: phase change materials. These are remarkable substances, the same kind you might find in a rewritable DVD. They have the unique ability to switch between two different physical states when zapped with a pulse of energy. In one state, the amorphous state, their atoms are jumbled and disordered. In the other, the crystalline state, their atoms are neatly arranged in a lattice. Crucially, these two states interact with light differently. One state is opaque, the other is transparent. The genius of the breakthrough was to combine these two ideas. Scientists built a photonic chip with a microscopic glass resonator, and on top of that ring, they placed a tiny speck of phase change material. Here's how it worked. A pulse of light, representing a piece of data, is sent into the resonator. As the light circles inside the ring, a second, more powerful laser pulse is fired at the phase change material sitting on top. This pulse acts like a write command. It can heat the material just enough to either snap its atoms into the orderly crystalline state or knock them into the chaotic amorphous state. It's like flipping a switch. Now, when the trapped light inside the ring interacts with this material, its behavior changes. If the material is in its transparent, crystalline state, the light continues to circle brightly. If the material is in its opaque, amorphous state, the light is absorbed and its intensity drops. By measuring the brightness of the light coming out of the resonator, you can read the state of the material. You can tell if it's holding a 1, bright, or a 0, dim. For the first time in history, light could both compute and store data within the very same physical space. The photons themselves were now part of the memory system. They could write information, and that information would stay there, held in the physical state of the material, ready to be read again by another pulse of light. Photons had gained memory. The barrier had fallen. The whisper in the wind had been given a voice that could last. To truly grasp why this breakthrough is so revolutionary, we need to understand a dirty little secret about the computers we use every day. It's a fundamental design flaw that has plagued computing since its inception, a concept known as the von Neumann bottleneck. In a traditional computer, the processor, the brain, and the memory, the long-term and short-term storage, are physically separate. They live in different parts of the chip, or even on entirely different chips connected by tiny copper wires. This means that for every single calculation, no matter how simple, data has to be shuttled back and forth. The processor says, "I need number A." A signal travels to the memory. The memory finds number A and sends it back. The processor says, "Now I need number B." The signal goes out again. Number B comes back. The processor adds them together to get C, and then sends a final signal. Store C in memory. This constant back and forth movement is the bottleneck. It's like an incredibly talented chef who has a tiny workbench and has to run to a giant pantry down the hall for every single ingredient, one at a time. The chef can chop an onion in a fraction of a second, but most of his time is wasted just running back and forth. In the world of computing, this running back and forth consumes a staggering amount of energy. Studies have shown that in modern data centers, nearly 80% of the energy burned by a chip is not used for actual computation. It's burned simply moving data from one place to another. We are spending most of our power on logistics, not on thinking. This is where photonic memory changes everything. With this new architecture, the processor and the memory are no longer in separate buildings. They are not even in separate rooms. They are the same thing. The light that performs the calculation is the same light that interacts with the memory, which is located in the exact same spot. The data resides precisely where the computation happens. This is called in-memory computing, and it eliminates the von Neumann bottleneck almost entirely. There is no more shuttling. The chef has all the ingredients right there on the workbench. The energy waste plummets. The speed skyrockets. The light computes exactly where the data resides. Fast, efficient, and without pause. This isn't just an incremental improvement. It's a fundamental rethinking of how a computer should be built. It's a shift from a system based on motion to a system based on co-location, and it unlocks a level of efficiency that silicon could only dream of. But the brilliance of light doesn't stop with speed and efficiency. It has another, almost magical property that electrons lack: color. When we see a beam of white light, we are actually seeing a combination of all the colors of the rainbow, from red to violet, all traveling together. Each color is just a different wavelength, a unique frequency of light. Scientists long ago mastered a technique for fiber optic communication called wavelength division multiplexing, WDM. It allows them to send dozens or even hundreds of different data streams down a single fiber optic cable simultaneously, just by encoding each stream on a different color of light. A red beam might carry your video call, a green beam your friend's email, and a blue beam a movie being downloaded, all traveling through the same glass thread at the same time without interfering with each other. Researchers have now brought this same principle to photonic chips. By designing resonators and logic gates that are tuned to specific wavelengths, they can turn a single photonic processor into a massively parallel computing device. Imagine a single lane of traffic on a highway. That's like a traditional electronic chip. It can only process one stream of data at a time. Now imagine that highway instantly transforms into a 40-lane superhighway, with each lane moving at the speed of light. That is the power of color in photonic computing. On a single chip, a purple beam of light can be working on one part of a complex problem, while a green beam works on another, and a red beam on a third, all in perfect parallel, side by side. You are not just getting one computer, you are getting dozens of independent computers operating simultaneously in the same tiny space. This multiplies the processing power of the chip, not by adding more components, which would create more complexity and heat, but by simply leveraging an intrinsic property of light itself. This parallel power is a perfect match for the demands of artificial intelligence, where problems are often broken down into thousands of smaller tasks that can be solved at the same time. With photonic computing, we can unleash a symphony of colors, a multi-lane highway of computation, to tackle problems that would overwhelm even the most powerful supercomputers of today. And that brings us back to the force that is driving this revolution forward with such desperate urgency: artificial intelligence. AI is no longer a niche field of academic research. It is the new engine of the global economy. It's shaping every industry, from finance and healthcare to entertainment and transportation. For the tech giants of the world, the Googles, the Metas, the Microsofts, leadership in AI is not just a matter of profit, it is a matter of survival. But, as we've seen, the energy burden of developing and deploying these massive AI models is becoming unsustainable. The cost of electricity and cooling for data centers is now one of a company's largest expenses. The environmental impact is a growing concern for governments and the public. There is a very real fear that we could reach a point where the cost of training the next, more powerful generation of AI becomes so prohibitively expensive that progress grinds to a halt. Photonic computing arrives as a potential salvation. It offers the promise of a chip that can handle the massive parallel workloads of AI with unparalleled speed, while consuming a tiny fraction of the power. Imagine a device that has the thinking power of a warehouse-sized data center, but uses the energy of a common desk lamp. This is the holy grail that tech companies are racing to achieve. For them, this is not a futuristic fantasy. It is an economic and strategic imperative. The first company to master commercial-scale photonic computing will not just have a faster chip, they will have an insurmountable competitive advantage. They will be able to train more powerful AI models, faster, and at a fraction of the cost of their rivals. They will be able to offer cloud computing services that are orders of magnitude more efficient. In the high-stakes arms race of artificial intelligence, the platform that runs on light is poised to win. While AI may be the immediate catalyst, the potential of photonic processors stretches far beyond it, out to the very horizons of human discovery. This technology is not just about building better chatbots or recommendation algorithms. It's about building a better tool for answering the biggest questions we can ask. Consider the field of medicine. Designing a new drug often involves simulating how millions of different molecules might interact with a specific protein in the human body. This is a computational problem of almost infinite complexity, often taking the world's most powerful supercomputers years to model just a handful of candidates. A photonic computer, with its massive parallelism and light-speed processing, could simulate these interactions in moments, dramatically accelerating the discovery of new cures for diseases like Alzheimer's, cancer, and more. Think about climate science. Predicting the long-term effects of climate change, or forecasting the path of a hurricane, requires modeling the entire Earth's atmosphere, a chaotic and interconnected system. Photonic processors could run these simulations with a level of detail and speed we can't even imagine today, giving us a clearer window into our future and a better chance to prepare for it. In astrophysics, scientists are drowning in data from new telescopes like the James Webb. Sifting through the light from distant galaxies to find new planets or understand the origins of the universe is a monumental task. Light-based computers could analyze this cosmic data in real time, decoding the secrets of the galaxies at the same speed the information arrives. The promise of this technology is nothing less than the acceleration of discovery itself. It's about shrinking the time between a question and its answer. Problems that currently take a lifetime of research could be solved in an afternoon. The light horizon is a future where our curiosity is no longer limited by our computational capacity. Yet, even a future this brilliant is not without its shadows. The path from a laboratory breakthrough to a world-changing technology is long and fraught with challenges. The dawn of the photonic age is not guaranteed. It must be built. The first major hurdle is scaling. It's one thing to create a single, perfect photonic chip in a pristine clean room. It's another thing entirely to manufacture billions of them cheaply and reliably. The entire global semiconductor industry, a multi-trillion-dollar ecosystem, is built around silicon. Rebuilding that infrastructure from the ground up for photonic components is a monumental undertaking. Then there is the issue of material wear. The phase-change materials that allow light to remember can only be switched back and forth a finite number of times before they begin to degrade. While they are durable enough for many applications, achieving the lifespan and reliability of traditional silicon memory is still an active area of research. And perhaps the biggest challenge is one of inertia. Our entire digital world is written in the language of electrons. Every piece of software, every operating system, every programming language is designed to work with traditional processors. Creating a new ecosystem of software and tools that can fully harness the unique architecture of photonic computers will require a paradigm shift in how we think about programming. But where there are limits, there is also opportunity. Where there are challenges, competition ignites. Right now, a global race is underway. University labs, ambitious startups, and the research divisions of tech giants are all vying to be the first to solve these problems. They are experimenting with new materials, designing new chip layouts, and writing the first lines of code for this new era. The shadows ahead are real, but the race to master the technology that could define the next century of intelligence is on. So, we stand at a profound turning point in our history. Inside a laboratory, on a chip smaller than your fingertip, light has learned a new trick. It doesn't just move anymore. It remembers. The age of electrons and silicon was not a failure. It was a spectacular success. It gave us the modern world. It connected our planet, democratized information, and laid the foundation for everything that has come since. But every great era must eventually give way to the next. Electrons built our digital age, but photons point the way beyond it, to a future that is faster, cleaner, and freer from the physical constraints that have held us back. One day, and perhaps sooner than we think, the most powerful machines on Earth may not just run on light, they may begin to think in it. When that day comes, we will look back and realize that the Silicon Age, for all its glory, was only the beginning. The story of photonic computing is more than just a tale of technology. It's a powerful lesson about the nature of problem solving. When we face a wall that seems insurmountable, sometimes the answer isn't to push harder, but to step back and look for a completely different path. Our innovators didn't just try to build a better electron, they abandoned the electron altogether and embraced the photon. What is the silicon wall in your own life or your work? What is the one problem you keep attacking the same way, only to get the same frustrating result? Perhaps the solution isn't a better version of the old approach, but a radical shift in perspective. Your very own photon. I'd love to hear your thoughts in the comments below. What do you believe will be the most transformative application of this technology? What grand challenge would you want to solve with a computer that thinks at the speed of light? Thank you for joining me on this journey to the edge of innovation. I hope it has sparked your curiosity as much as it has mine. And if you enjoyed this exploration and want to see more stories about the future we are building, please consider hitting that subscribe button and joining our community. We have many more journeys to take together.